Okay, so we're nearing the point where we will be able to get the friction factor for turbulent flow, and using the Darcy-Weisbach equation, we'll be able to figure out head loss for turbulent pipe flow. So we're looking at turbulent flow. And what we're going to do, we're going to use the velocity profile that Millikan came up with in 1937, and that was for the velocity profile in the overlap region. So this was the region where both laminar shear stress and turbulent shear stress were important. And we need to do a transformation here of the coordinate system. Millikan was doing this for flat plate boundary layer or channel flow. But what we want to do is we want to transform the y coordinate into a radial coordinate. And if you think about at r equals capital R, that would be, so if this is our pipe and we have the pipe wall there, so that's the thickness. So we have a little r here, and out here, this is little r equals capital R, and that would be the radius. So looking at it in this manner, if we have r minus r, so on the outer wall, so at r equals capital R, we get y equals 0. So basically what we're doing is we're retransforming that so that this is kind of like y coming in that way, away from the pipe wall, which is what it should be for pipe flow. And the relationship that we will use is the one that Millikan proposed. Now, one thing that I should say is even still to this day, people are debating these profiles and the constants and the universality of the relationships that result. People are arguing whether or not this relationship would apply to flat plate boundary layers or open channel flows, or what the coefficients are. That's all taking place because we're getting better and better data enabling us to be able to study this profile in more detail. For the purposes of what we're doing here, however, we're not really going to worry about that because the main thing that Prandtl and von Karman and everybody else who studied this were trying to do, where they were trying to come up with a functional relationship with which to collapse experimental data. And that's the approach that we're going to take. So we're going to use Millikan's profile, this one here, and with that, we're able to calculate an average velocity. I'm not going to go through the math. I'll just show the final result of that. The U star, remember that's the friction velocity. U star is tau W over rho square root. Okay, so we have that, and the constants that we're going to use here, although they can be tweaked, as I mentioned before, we'll use these ones, which were the ones that Millikan originally had. Now with that, what we can write is the average velocity divided by the friction velocity is approximately okay, so that's where we get to. What can we do with that? Well, it turns out that we can actually do quite a bit, and we're going to focus in on this term here, and we're going to take the friction velocity from up here, and we're going to rewrite that in terms of our friction factor, which is what we're after. And the friction factor relationship came out of our early dimensional analysis of this problem a few lectures ago. So rewriting the left-hand side, and here we have our wall shear stress. This came out of the dimensional analysis, and so with that, we're able to continue on and rewrite this in terms of our friction factor, F, which is a good thing because that's what we're after. So that means we have friction factor on the left-hand side of the equation. Let's get it on the right and we'll be in business. So taking a look at the right-hand side, we're going to work on the term that was in the natural logarithm. Now I'm going to play a little bit of trickery here. I'm basically introducing a V and a V. I should be a little careful. This here is kinematic viscosity. So don't get that confused with my V's. Hopefully you're not. That's a V, that's a V. I've introduced it into the numerator and denominator so that we can simplify this a little. And what we're going to do, we notice that the first term is 1/2 of the Reynolds number based on diameter. And then we have the friction factor, which is what we're after. And with that, we can then rewrite Millikan's velocity relationship. And we get something that looks like this. And I've now transformed from a natural logarithm to a base 10 log. So this profile is something that Ludwig Prandtl came up with in 1935. So he adjusted the constants to provide a better fit, and that will be the next equation that I will write. So Prandtl further reduced that or recast it in the following form. Okay, so we have this relationship here, and this is good because we're getting something that has the friction factor in it, has the Reynolds number. It is a transcendental equation, meaning that in order to solve it you have to iterate because the friction factor appears on both sides. There was one other contribution that needed to be added, however, and that had to deal with the fact that not all pipes were smooth. Some pipes are rough, and consequently we needed to take into account the pipe roughness effects. That's what we're now going to do. It's a bit of an adjustment to this equation. So it turns out for turbulent pipe flow, the pipe wall roughness has an impact on the friction factor. And we can classify the surface roughness based on a ratio which has our friction velocity in it. So in a way this is kind of like a Reynolds number when you think about it, because we have a length scale and we have a velocity and we have the kinematic viscosity in the denominator. But if that number is less than 5, that would be a hydraulically smooth pipe. If the number ranges between 5 and 70, the number being our length scale times the friction velocity divided by the kinematic viscosity, this is transitional. And it results in moderate Reynolds number effects. So what's happening here is as you increase Reynolds number, it will have a moderate impact on our friction factor F. And then finally, if this number, which is basically a Reynolds number for our roughness, if it is greater than 70, actually let me write that over here. If it is greater than 70, then we have what we refer to as being fully rough flow. And here we can see the friction factor is independent of the Reynolds number. So with that, you can integrate that in, and that basically modifies Prandtl's equation to include surface roughness, and what we end up with is the famous Colebrook-White equation, which is used for estimating the friction factor in turbulent pipe flow. Again, it's a transcendental equation, meaning that you need to iterate if you want to solve it. And it's sometimes referred to as being the Colebrook-White equation. Very famous one in fluid mechanics. Now, this equation, you can either solve it directly by going through the trial and error iteration, or you can go and look at plots of it. And this is plotted in the Moody diagram, which we looked at earlier for laminar flow. So what we're going to do, we're going to go back and take a look at the Moody diagram, and we're going to look at what happens when you have the Moody diagram and you add pipe data for increasing roughness of pipes. So let's take a look at that now. So what we have here is Moody diagram with the laminar flow curve on it, and then we have smooth pipe curve. You can see it there, and then we start putting curves with variable epsilon over d, so surface roughness, and we have the smallest surface roughnesses, and then we have it increasing, and as the surface roughness gets bigger and bigger or greater and greater, the friction factor goes up, which we would expect, and then finally with very, very rough pipes. And so that is the Moody diagram. That's a diagram that we use quite extensively within mechanical engineering in order to give us the friction factor and estimating the pressure drop within pipe flow. Or you could estimate other things. You could be doing sizing and determining the diameter, or you could be determining the volumetric flow rate going through a given pipe flow configuration. So with that, we're almost at the end. We come back to the Darcy-Weisbach equation, enabling us to come up with an expression for the turbulent head loss, which is what we would use in the energy equation. So if you remember back, we looked at the Darcy-Weisbach equation, and all we do here is we put in the value of the friction factor for turbulent flow that we either get from the Moody diagram or from the Colebrook-White equation. And we get that. Now, there is one final relationship that I want to leave you with, and this is an approximation for the friction factor that does not require the iteration due to the transcendental nature of the equation. And so this is an approximation. And so with this equation, and you'll notice there is no friction factor on the right hand side of the equation. This would give you a starting point perhaps by which you could estimate the friction factor, and then after you get it from here you could go to the Colebrook-White, and then you'll be closer to being converged. But anyways, that's another relationship that you can get the friction factor for turbulent pipe flow from. So that concludes friction factor. We've looked at friction factor for laminar pipe flow, and we looked at it for turbulent pipe flow. We came up with different relationships, Colebrook-White, the analytic expression for laminar flow, and finally the Moody diagram. Those are all things that you can use when you're solving pipe flow problems in engineering.